we're telling an interesting story about a transformation of a product through a new design and a new manufacturing process. What we're looking at is a optimized transfer case for an electric vehicle. The overall challenge of this project was to find a way to minimize the noise coming from the transfer case on the electric vehicle because, as you know, electric vehicles are quieter and we tend to hear everything. So there was some vibration causing a noise. So we went through an entire process to look at how can we re-engineer this with a more modern manufacturing process like additive combined with CNC machining in order to get the optimized design. The optimized transfer case is basically been installed in this little electric vehicle, this little e-car that we have over here. If we come around the back, we can see here that our team member Matthias Leinberger installed the transfer case directly into this car and was actually able to drive the vehicle in here with it. And so we'll tell the whole digital story on how we re-engineered this, the manufacturing process, produced it, and actually got it assembled into the vehicle. So we'll start our digital journey at these two stations here, the engineering and simulation and the generative design and 3D printing stations. And here we're using NX and SimCenter 3D in order to re-engineer the transfer case. The whole process started with a test, a physical test, using our software to collect the test results in order to be able to digitally understand where the vibration was coming from, which was leading to the noise. On this slide, what we're basically looking at is we're looking at the test results, and we're able to visualize those test results in the product to understand where the excessive vibration was coming from. And we can use different types of CAE analyses to be able to analyze the digital version of the part to also virtually understand and pinpoint where issues are. We can look at strength, mechanical strength. We can look at thermal characteristics. We can look at flow. We can even look at NVH. And in here, we're kind of looking at all of these as inputs into the system to understand how our digital model is performing in the real world. Based on the results that we collected from our analyses, we were able to see that there were some opportunities to improve the design. There were some areas where we could increase strength by adding more material. There were some areas where we could move material into different locations of the part in order to be able to eliminate the vibration that we were running into. We took some of these results and some of the areas of software telling us needed attention, and we could feed that into our design optimization system, our design optimization capabilities inside of NX. We have a topology optimization tool, which basically looks at different load paths that run through the model and gives us feedback on whether or not we might need to increase the load based off of the different forces that we're trying to achieve, the targets that we're looking to set. And the system will come back with a new model that has been optimized for the target results that we're looking for. And so NX was able to do that with our NX topology optimization. So we're looking at NX design for additive manufacturing. What we're looking at is our transfer case model. In blue, we're looking at the design space that we've identified where we would like to have the topology optimization tell us where the material needs to go. And then we're basically setting up the loading conditions that we would like to have NX solve for with regards to where to put the material in order to achieve those loading conditions. And so now what we're basically looking at is NX running through the solve, and now we're seeing where the geometry needs to be created and where the material needs to be in order to be able to achieve those conditions. Now that we've finished with the topology optimized design, we're going to start to think about our manufacturing process. And in this case, we're going to 3D print the transfer case. We're going to 3D print it because of the fact that we would like to reduce the amount of time that it's going to take, and some of the geometry that we've created here would create some challenges if we were going to try to machine it. And so in this case, we're going to 3D print it, which gives us a bit more freedom and flexibility on the shapes that we're able to manufacture. In this case, we're basically still continuing to use NX, But now we're in the NX additive manufacturing product where we're basically setting up our powder bed fusion build preparation. And so we've basically put the part into the build, and we're going to look at how we would like to orient the parts, and based off the direction that we're going to print, we can add the support structures. And then this is where things get really interesting. We can use NX to be able to analyze the build process and simulate how the build process is actually going to perform to help us understand if we need to make any adjustments to the geometry in order to get a high quality print to the tolerances that we need when we go to the printer. And so here the simulation is telling us, basically that there's going to be some deformation that's going to occur, and the system can automatically compensate for that deformation by modifying the shape of the model in order to give us the correct physical print when we get to the shop floor. So basically, it's a digital twin of the manufacturing process that we're running through a simulation. Okay, so now we're looking at some additional steps downstream in the manufacturing process, and we're looking at simulation of the machining of the part that we 3D printed. I think one of the really cool capabilities within our Siemens portfolio and our solutions that we offer through NX and SimCenter for design and for manufacturing is the fact that it's a digital process and a single system that allows the engineers, the designers, the manufacturers to all work together and collaborate. I think the other important factor is the fact that we're working with the same data in the same system, so we're able to move the data through each of the process steps without losing any information. And then on top of that, the system really allows us to create a digital twin of the different steps of the process to look at the design or look at the manufacturing process or understand how our design is going to perform in the real world and connect that information to what's actually coming off the physical product or the machine itself as we manufacture the process. So I think there's a lot of benefit in looking at the system and trying to take advantage of it in order to be able to shorten the amount of time it takes for companies and individuals to basically design and engineer and produce the parts that they're looking to create. But basically what we're looking at here is we're looking at our NX CAM NC programming software product, which is connected to the Run My Virtual Machine, which is basically the Cinemeric controller software that is used to control the CNC machine, the actual controller software. We're looking at both of these on the same machine where the controller software is driving a digital twin of the manufacturing process inside of NX CAM. And this is the most powerful way to be able to virtually simulate the manufacturing process to understand exactly how the machine tool is going to machine the part. So if we find any issues here, any alarms, any potential collisions, any strange behavior of the machine, we'll be able to identify it here in the virtual world, optimize it out, correct it before we actually send the G code to the shop floor. So we spent some time talking about what happens in engineering, but now we've come all the way over to the shop floor. And so all of that information and all the data that we created in engineering and manufacturing engineering, we're going to execute in production, and we're going to do it directly on Siemens hardware that's connected to a digital twin of a machine. And so in this case, we're looking at the Cinemeric One controller that is going to basically drive a digital twin of the process and of the machine. So we can come over to the controller, we can go ahead and hit cycle start, and basically here we're running the G code that we generated back over in the other station in NX CAM directly on our digital twin of the manufacturing process. It is the file that we created, and we're basically looking at the real performance of what this machine is really going to do if it was connected to a real physical machine. Now, one more really cool kind of capability that we have in our portfolio, we talked about it before, where we have our digital twin, where we have NX CAM connected to the Cinemeric Run My Virtual Machine software. So we're basically running NX CAM over here with the controller executing the G code, but in this particular case, we're actually doing this with a robot that has been equipped with end effectors that allow it to do both 3D printing, FDM style, as well as CNC machining. And so then over here, we're basically kind of telling a story about how we created a composite layup mold for the hood of our electric e-car over here. Basically, the demonstration is showing one of our Siemens centers, the Impact Center in Erlangen, Germany, where we have this Kamal robot actually doing the 3D printing and the machining.